Two-dimensional Fourier transformation, linking observations with theory. This is one of my favorite lectures. I really like this lecture because lots of reasons. It relates equations. It relates the equations to pictures. It relates observations to theory. And the data, it has real data and it's real. It's real Earth soundings and they're typical Earth soundings. One more reason I like it, there's some fun exercises after you see what the data set is. So let's dig up some data. And here it is, some marine seismic soundings. Here's the distance on the x-axis. The scale is at the bottom here. It goes from 0 over to 3 kilometers. And 3 kilometers, you will understand if you're American that this is 2 miles. And we're looking at echoes inside the Earth, underneath the ocean, and the time axis runs from 3 seconds. That is to say, there was an explosion on the surface. The first 3 seconds we're not showing you, there's nothing to see, and we are looking at from 3, and here you see 4 seconds. Looking at 1 second of data. There's going to be a ship, and the ship is going to sail along, and the ship is going to start about here. If I can draw a ship, we'll start about here, and after about a half an hour, running at about 5 knots, our ship will be over here, and the ship has a gun. The gun shoots off. The ship is actually higher up. It shoots off, and the first reflection comes from the water bottom. Then we get later reflections from these layers in here. Then we get still later reflections from these bumpy things at the bottom here. So the layers, we're calling this the sediments, and we're calling this bottom broken up stuff the volcanic basement, because things are going in a whole bunch of different directions down here. Calling these layered sediments in here. Okay, let's take a look where this data might have come from. Here's a picture of the Earth. And there's this fascinating crack along the surface in the middle of the ocean. I'll try to indicate it for you. It's between these two lines. I'll kind of trace along this crack. This crack is called the Mid-Atlantic Ridge. Notice all the roughness near it. This crack goes on and on, almost to Antarctica, and it starts maybe above Iceland. Get out your Google Earth, as I did, and you'll get to see this crack, and you can look at a lot of more cracks on the Pacific Ocean. So what's happening? Lava, volcanic rock is bubbling out on this crack, and it squirts out into the ocean and immediately congeals into something called pillows or other things. And so you see all this roughness. So there's no sediments out here. It's nice fresh rock, and this is pulling apart. The ocean is spreading the continents away from it. But as we get out here, things smooth off because there's dead fish dropping to the bottom of the ocean. And there's also rivers here which are bringing out sediments. And the wind is blowing off Africa and it's pulling out sand dust. So we have sediments closer to the continents. This data is really very simple. Things get much more complicated as you get near the continents. And if you'd really like to see some interesting complications, go look down here in the Gulf of Mexico and many other places on Earth. Well, Venezuela, you might know, is down here. Okay, so this data that we're seeing here is rather typical. This whole big region here may look like this data that we have on the side. Okay, let's go on and talk about it some more. I'm showing you a tiny piece of data. My vertical axis here, my time axis, has only 128 points. It looks a little bit pixelated along the water bottom. Originally I had 256 points, but I reduced. I want you to see each pixel if possible. And I chose only 64 points along the space axis. Now in real data, we will typically have like 2,000 points on the time axis, so things will be smoother on time, and there'll be a much longer axis on time. Might go out to 8 seconds, at 2 to 4 times the density of sampling we see here. And space, well, the space axis in reality is really complicated. What I'm showing you is rather old data with a very simple space axis. So what's the space axis really look like? Well, really, the shot can be anywhere on the Earth's surface. That is the air gun, the compressed air that bubbles out and initiates the source of the echoes. So that can be anywhere. So we got 2 axes here. And our recorders, our hydrophones, we got 2 axes here. Then, of course, we've got the time axis here. So we really have a 5-dimensional space we're playing with in data. And in the end, we're going to produce a 3-dimensional space in function of trying to make XYZ Earth volume. Okay, so how do we do the computation? That will be the next lecture. Okay, we'll see you then.